different quantum systems, systems that obey quantum mechanics, systems that exhibit quantum mechanical effects, and then use them for other tasks. Some tasks might be things like quantum computation. Other tasks might be things like quantum sensing. So we were talking a little bit earlier about like those squeeze states, and what we saw upstairs is how they do that in the optical regime. If I want to do like use quantum states of light that have properties for sensing, that have quantum correlations, different entangled states that can be used for quantum imaging, quantum radar.
And
like
in
this.
terms of real world, tell me.
These are real things.
So
In the future, potentially, maybe. Like right now, yeah, one of these kind of systems is being used to enhance the accuracy of light of the gravitational wave observatory.
Okay,
Yeah,
good.
the next generation of them are using quantum enhanced sensing, quantum squeeze states of light.
I hear a sound behind us. What is that?
The sound behind us. So what we want to do here is we want to make a quantum system on a superconducting circuit. So what we have is just on top of some silicon, a circuitry made out of aluminum. And we're going to cool that aluminum down to the point where it becomes superconducting.
Uh-huh.
Yeah. And for aluminum, that means cooling it below 1.2 degrees Kelvin.
You're right.
Yeah. So that sound you're hearing is basically us pumping two different isotopes of helium together to get to that temperature.
Uh-huh.
So liquid helium is about the coldest liquid we have. Hydrogen, no one's going to mess around with liquid hydrogen because it's very reactive. Liquid helium is the coldest safe thing we have. And it gets down to 4 degrees Kelvin, which is not cold enough. So if I just kept my my chip and just poured liquid helium on it, it would not reach superconducting temperature. What I need to do is I need to make a fridge. I need to pump two different kinds of liquid helium together. So helium-3 and helium-4. Once they mix together, I can pump on them the same way that I pump on Freon in a regular refrigerator. And by letting them expand and actually physically compressing them back down to the liquid form, I can get cooling below 4 degrees Kelvin. In these cases, it gets down to 5 millikelvin.
That's awesome. Yeah.
And so what it looks like inside is something like this. So both of them are closed right now because they're both running experiments at the moment. But we get down to 5 millikelvin only at the very bottom. So it's actually kind of tiered in layers like this. Up here, you'll have most of the control for the refrigerator. That's okay if it's warm. Down here, you'll have more of the control for the actual circuitry. So microwave electronics to talk to the circuitry, things like that. They have to stay cold, but not necessarily 5 millikelvin. Down here, that's where you keep your chip. That's where you keep everything that needs to be incredibly cold. You're going to wrap that in conductive material to make a Faraday cage so that external magnetic fields and electric fields don't interfere with it. So that's kind of what it looks like with its shell off.
Tell me something. Is there a typical scientist who work here?
Sorry?
A typical scientist. What would you say is your typical scientist who
would
want to be involved in this kind of work?
Well, the typical scientists who work here are mostly physicists and electrical engineers. So right now what they're doing is a lot of work in the nanofabrication facility in the clean room, actually designing these circuits. These circuits have very high sensitivity. They're not something that I can just make on my workbench. I need to work in a very, very clean environment to get very, very high precision so that they meet all the specifications they actually need to meet.
Yes.
They're very complicated structures. Not complicated in the sense that you can't understand it, but complicated in the sense that I need the right tools.
I saw them were really masked up. Totally masked up. Is that over in the other lab?
You have to wear a whole bunny suit to actually go and build them. So that's one of the types of people that works in this lab. Another type of person will be the one who actually designs the circuitry to talk to those circuits. So they won't work in the clean room, they'll work mostly in here. Yeah. And that's where a lot of the electrical engineers come in. And also you need physicists as well, because most of the experiments end up being quantum mechanical in nature. So things like tests of circuit quantum electrodynamics, things like generation of microwave single photon states, things like quantum computing. So that's where the physicists really kind of shine.
Okay. And I see some diagrams over here, for example.
Yeah. So those will be some...
You're a journalist.
Yeah, and we see kind of a mix here. I guarantee this was made by a physicist. Probably that as well. This one looks like engineering. But of course, it's not a clear line. The people working on the electrical engineering work maybe physicists by degree, people working on the physics work, maybe electrical engineers by degree. I wouldn't even be surprised if like a chemist somehow wandered their way in here.
That's right. That's interesting.
Yeah.
How people have to be able to collaborate for a product.
Yeah, and like that's just people working physically in the lab. What they'll often do is get experiments from people in different fields as well. Like if I want to design an interesting experiment,
Yeah.
sometimes that comes out of being in the lab and actually working at it and like figuring out what the machines can do and asking questions about, okay, can they then do this next step? Sometimes it comes out of looking at a just general, say, a math problem and wondering, like, does this represent a physical system? So that's
Okay.
where mathematicians and theoretical physicists come into the equation.
That's awesome.
Yeah.
It's great. Tell me, how were you interested in this?
How did I get interested in this? So I was a laser physics guy. I'm a laser jock. I love lasers. I love playing with them. I love optics. And it came from just trying a bunch of different things. So
You were curious.
Yeah, I did a co-op program when I was an undergraduate, so my background is in physics. And I did a whole bunch of different things. I did theoretical physics for a while in one co-op area, and I liked it. I enjoyed the math of it, and I could not keep myself focused, honestly.
Yeah.
I needed something that I could play with my hands. I like the math. I like the concepts. I had a hard time staying on track.
What would you say to students?
Just keep trying different things. You don't know. Don't get too locked in on what you want to do. Keep trying different things. It's never too late to change what you want to do. But so just try to get as much experience as possible, and you'll find something you like in it.
Thank you so much, John.
Thank you.